I hope you took a crack at the question that I just posed, and now I'm going to provide the solution. But not only am I going to provide the solution, but I'm also going to use it to derive the most common representation of the differentiation equation, which is this here. All right, so our question was to use the same function as before, y equals x squared plus 2x plus 2, and find the slope of that curve where x is equal to -1. So let's start off by setting x equal to -1, specifically x1 for our point P, and then we'll calculate the y value, y1 for our point P. So at the point where x is equal to -1, y is equal to 1. So point P is located at -1, 1. Now let's use the same very small delta x as we used in the last example. So very, very close to 0, y times 10 to the -6. And then add that delta to x1 to give us our x2 value, our x value for our point Q. And to calculate the y value for our point Q, we can throw x2 into our function f. And there we go. So a quick aside here, pertinent to defining differentiation in its most common equation representation, an alternative way to calculate y2 here is to put both of these steps into one. So x1 plus delta x, so denoting that as x plus delta x, and just putting it into our function f right away instead of in two separate steps. So by doing both of these steps as a single step, moving x1 plus delta x in where x2 was in our function, we of course get the same y2 value as we did when we did it in two separate steps. And clearly our point Q, which is at this point here, is extremely close to P because our delta x is so small. Now we can calculate the slope between those two very close points using our same slope equation that we've used a number of times in this notebook recently, and that comes out to 1 times 10 to the -6, which is very close to 0. Therefore, I already feel comfortable saying that as x2 becomes infinitely close to x1, as our delta x becomes very small, infinitely small, it becomes clear that the slope m at x is equal to -1 is equal to 0. And we can use the same formula as we used earlier to calculate our y-intercept b, and then to plot our line, mx plus b, and we can put that on our curve and see, yes, this point where x is equal to -1 is the point where slope is equal to 0. It's the point where our curve stops going down and starts going up from either direction. It is the minimum of our curve. All right, so we've now come up with a solution to the question that I posed in the preceding topic. Great. But now let's go further to come up with that specific definition, the most common representation of the differentiation equation. Let's continue onward to come up with this. So I've said this a few times, but let's look at it mathematically. As Q becomes infinitely close to P, x2 minus x1, the difference between the x values of P and Q, approaches 0. In other words, the difference between the x values, delta x, approaches 0. Now, that approaching, we've already learned about limits. Well, now we can use that limit notation to denote where the difference, the delta x, is approaching 0. It's a limit approaching 0. At this point, using the delta method that we've been using together, and then you might have even used on your own to come up with the solution to this problem here, we've derived the definition of differentiation from first principles, from examining how, as 2 points become very close together, that slope between the 2 points represents the derivative at that point in the curve. So we can denote the derivative of y with respect to x, where we denote derivative of y as dy, and the derivative with respect to x as dx as dy over dx. So this just means the derivative of y with respect to x. So, the derivative of this slope of y with respect to x. And so that derivative, dy dx, is equal to delta y divided by delta x, where delta x is approaching 0. So this is all we've been doing. In all of the examples, we've been using code to calculate delta y and delta x, and then we've been making the delta x smaller and smaller and smaller until it's clear what the slope is, and that slope is the derivative of y with respect to x. So to get a little closer to this most common definition, let's expand out delta y to y2 minus y1. So we already knew that from earlier. We knew that delta y is equal to y2 minus y1. So that's an easy substitution to make. And then finally, by replacing y1 with fx, so y1 is simply a function of x1, so that's an easy replacement to make here. And then replacing y2 with a function of x plus delta x, just as we did earlier on here in the code. That's the same thing that we're doing here now. We're replacing y2 with the function of x plus delta x. And now, by making those two substitutions, we now have the most common representation of differentiation. So this is the same formula as I showed you initially on this slide here and said I would explain how we get to this, and now we've done it. So let's observe now this differentiation equation in action. So I'm going to create a function here called differentiation demo, diff demo, and into it we pass in our function that we are differentiating. We pass in the x value that we would like to differentiate at, and we pass in some delta. So we're going to start with a large delta, a large difference between x2 and x1, and then we're going to decrease it and see what happens. So before we jump to actually using this diff demo function, let's cover exactly what's in it. This is the same formula as we have here, the same fraction here. So it's on the numerator, in the numerator, we have f of x plus the delta, f of x plus the delta, minus the f of x, minus the f of x. And then in the denominator, we have simply the delta. So this differentiation demo function covers the fraction here. Now let's use a number of delta values to capture this gradual approaching of a very small difference between the two x values, a very small delta x. So to do that, let's have a bunch of delta values getting gradually smaller and smaller and smaller and smaller, approaching 0, approaching 0. And for each of those, whoops, I need to run all the code, of course, to make this work. So let's try that again. So we can see here that with our function f, passing that in to our function, and saying to try to find the slope at x is equal to 2, we can now pass in different delta values, and as those get smaller and smaller and smaller, we get closer and closer and closer to our slope at the point of x equals 2 of 6. So this is the same that we got earlier when we were kind of more manually calculating using the delta method. And same thing at x equals 1 for the question that I posed to you earlier that you could have solved on your own. At that point, x equals 1, same thing with our function f, and our delta is getting smaller and smaller and smaller. Our slope converges closer and closer and closer towards 0. Awesome. So now we've used limits and the delta method to come up with the most common equation for differentiation. Up next, we'll go over a couple of different ways that you can notate differentiation. And after that, we'll start digging into rules you can use so that you, by eye, can, in a lot of situations, calculate derivatives without having to use any code at all.